In week 6, we still talk about relativity, but um, in a different context to last week. Last week we were talking of relativity in the context of space and time. Now we will be more interested into energy, momentum, and also particle physics. So we'll start this week with some revision about how we name and write atomic nuclei and atoms, and how we specify some radioactive decay process, and also we have a section about units. Then we talk of something very important about energy and Lagrangian. So Lagrangians we introduced in action physics come back here in relativistic framework. And we also use this as a pretext to introduce Hamiltonians, uh, which is a fancy name for energy. So as a first approximation, you can take Hamiltonian equal energy. We motivate a relativistic expression for the Lagrangian, which can be used in, for instance, in Euler-Lagrange equations. And we also obtain a relativistic energy from the expression of the Hamiltonian. And of course, that will give us the famous equation E equal mc squared. We then get a very useful relation between energy and momentum, which we can use for relativistic kinematics. And we also show that in relativistic process, because of this equivalence between energy and mass, mass is not necessarily conserved. We then move to particle and interaction. So we are still in relativistic framework. Particles physics always, most of the time, require relativity. So we use relativity in the context of particle and interaction. So there is, in this section, lots of material, lots of videos, but be reassured they are relatively simple and straightforward, and mostly about the phenomenology of particles and interaction. There is very little equation in these videos. So we first introduce fundamental interaction of the standard model, why we need relativity in particle physics, energy and momentum. We introduce antiparticles. We explain how we can have attraction or repulsion between particles in the context of fundamental interactions. We introduce basic electromagnetic process, a strong interaction, the important concept of strength and range of interactions, how far they can go. We discuss radioactive decays, and in particular the beta decay and the electron capture. Q value is just a way to express energy conservation, which is relatively useful. We discuss neutrinos, how they were discovered, and what are their implication and in the standard model, their role. The W and Z particles, which are the mediator of the weak interaction.